When utilizing data, it is often important to determine the relationship between two variables, such as the height of a tree and the average number of leaves per branch, or the size of a tennis racket and the speed of the ball it hits. With data that falls on a straight line, the relationship between two variables can be easily found. In this case, every value of A has exactly one corresponding value of B. However, we rarely ever see this kind of pattern in real life.
More commonly, we see a pattern similar to the one on this scatter plot. The data do not follow an exact linear pattern, but we can instead find the model that is closest to the actual relationship. The equation y equals x plus 100 might seem to accurately represent the relationship, but how would we know if this was any better than y equals 0.95x plus 110? How do we decide which equation models the relationship best? One way to find the best model is to find the least squares regression line. For an example, say we are dealing with the simple data set on this scatter plot. For the equation b equals 0.5 times a, the sum of the squared distances between the observed and predicted values is 2.25. However, for the equation b equals a, the sum of the squared distances is 2. If the slope of the line is over or under 1, the summed squared distances is greater than 2. Thus, we can deduce that the least squares regression line is b equals a, which visually appears representative.
We can find the least squares regression line with this wonderfully efficient equation, where y bar is the mean of the output variable, x bar is the mean of the input variable, s sub y is the standard deviation of the output variable, s sub x is the standard deviation of the input variable, and r is the correlation coefficient, a measure of the strength and direction of the linear relationship between the two variables.
If we apply the equation for determining the least squares regression line to the data shown before, we get the equation y equals 147.875 plus 0.874 times 14.721 over 11.937 times x minus 52.25. Simplifying the equation to standard form, we get y equals 1.078x plus 91.55. Visually, we can see that our model does appear to accurately represent the relationship in the data.
Well, I hope you see the power of the least squares regression line. With it, we can make predictions concerning any kind of linear relationship. My name is James, and thank you for watching.